You've probably heard that Bitcoin is supposed to be the simple, really predictable system. But if that's true, how does it handle complex rules and agreements? Well, today we're going to dive into the conditional logic that really acts as its secret superpower. It's the hidden intelligence inside what a lot of people call dumb money. And that right there, that's the central puzzle. See, Bitcoin's core design values simplicity. It's meant to be dumb on purpose, so you don't have these complex programs running wild. It's kind of like a calculator that can only do basic math, right? So how do you get that to solve a complex problem without adding a bunch of new risky buttons? How does it handle these sophisticated if this, then that scenarios for our money? So this brings us right to Bitcoin's big programmability puzzle. Because on the one hand, you absolutely need advanced rules for some transactions. I mean, think about things like corporate spending policies or maybe trust funds that only unlock after a certain date. But on the other hand, if you add too much programmability, you're just opening the door to dangerous bugs and maybe even network-breaking attacks. Yeah, the challenge is finding that perfect sweet spot. You want to give people powerful tools, for sure, but you absolutely cannot allow a script to get stuck in an infinite loop or do something that could crash the entire network. And Bitcoin's solution to this is actually incredibly elegant. It allows for some powerful decision-making, but it does it in a way that is always predictable and, most importantly, is guaranteed to finish. Okay, so let's get into the nitty-gritty. Let's look at the core tools that Bitcoin script uses to make these decisions. We're talking about three fundamental commands, or opcodes as they're called: if, else, and ENDIF. Seriously, these are the essential building blocks for all the smart logic that we're about to explore. The best way to think about this is like a fork in the road. The script gets to the if statement and it has to check a condition. If that condition is true, boom, it takes path A. If it's false, it's forced to take the other path, the else path. And this is a really key point. The script can only take one of these paths. It can't do both, and it can't turn back. Both of those roads eventually merge back together at end if, and the script just continues on its way. And of course, it wouldn't be complete without an opposite, right? If has a direct counterpart, not if. And it's exactly what it sounds like, where if runs a block of code when a condition is true, not if runs its code when the condition is false. It's just a super handy tool for clean, if not this, then do that logic, without needing any extra steps. Now, using if and else works perfectly fine, but let's be honest, sometimes it can feel a little bit clunky, especially for simple checks. But thankfully, Bitcoin has a much more elegant and efficient tool for the job, a special class of commands that all end in verify. Let's see just how much this cleans things up. This is the perfect way to think about it. A verify command does two things at once. It performs a check, and if that check fails, it immediately terminates the entire script. Done. No second chances, no else path to fall back on. It is a one strike and you're out roll, and it makes scripts so much more direct and way easier to read. Okay, take a look at this. Let's say we need to check if a digital P is the right one. This is the long way to do it. It involves a whole bunch of steps. First, you have an operation called OP equal that checks if the key you provided matches the one required. Then, an if statement has to check the result of that test. I mean, it works, but it feels a bit roundabout, doesn't it? Now look at this. Look how much cleaner this is with the verify shortcut. A single command, OP equal verify, checks if the keys are equal and immediately fails the whole process if they're not. But if they do match, it just moves straight on to the next step, checking the signature. It's cleaner, it's more efficient, and what it's trying to do is just crystal clear. All right, so we've seen the individual building blocks. Now let's see how this all comes together to create a real-world script, one that offers two completely different ways to spend the very same funds. This is where the power really starts to become obvious. So imagine this scenario. You want to set up a payment where your business partner can spend the funds right away, but if they don't do anything for, say, 6 months, you want a backup key to be able to get those funds back. That is exactly what this time-locked fallback script is designed to do. So here's path A, the main spending route. When the business partner tries to spend the money, they provide a little piece of data that makes the initial OPIF condition true. The script then follows this path, and now it has just one job left. Use OP checksig to verify their digital signature. If the signature matches their key, the money's theirs. Simple as that. But what if that initial piece of data isn't provided? Well, then we fall into the OP else block. This is our backup plan. The script first texts the date with OP checklog time verify to make absolutely sure those 6 months have passed. If they have, it then moves on to check for a valid signature from your backup key instead. This ensures only you can get the funds and only after the deadline. And finally, ENDIF closes the whole conditional block. So the really crucial point here is that we've created a single script with two completely separate and secure spending paths. One for your partner, available right now, and one for you, available only after that time delay. And it's all thanks to that simple if-else structure. Now, this is all incredibly powerful, which probably brings up a great question. Why can't we just keep nesting these conditions and create scripts that are, thousands of lines long? And the answer is that Bitcoin has very strict built-in safety rules to prevent that exact thing from happening. First up, there's a hard limit on the physical size of any script. It cannot be more than 10,000 bytes. This is to stop someone from creating some gigantic script that would cause blockchain bloat and just be a pain for all the computers on the network to process. Next, there's a limit on memory. As a script runs, it uses this temporary workspace. You can think of it like a digital scratch pad called the stack. Well, Bitcoin limits how much you can write on that scratch pad to just 1,000 items. This prevents any single script from completely hogging a computer's memory. And finally, there's a limit on the number of actual commands a script can perform. Now, the exact number can vary a little, but it's capped at roughly 200 operations. And this is probably the most important rule of all for making sure that every script finishes executing almost instantly. So when you put it all together, you can see these aren't just random numbers somebody picked out of a hat. Each limit serves a vital security purpose. Their combined goal is to make the network robust by preventing what are called denial of service attacks, where some malicious person tries to slow down or even crash the network with transactions that are way too complex. So let's pull back for a second and look at the big picture. All of these rules, the conditional logic, the verify shortcuts, the super strict limits, they all serve a core design philosophy that carefully balances expressive power against absolute predictability. The technical term for this is Turing incompleteness. I know, it sounds like a weakness, right? But in Bitcoin, it's actually one of its most critical security features. It's a formal guarantee that any script, no matter how clever it is, will always finish running in a predictable amount of time. There are no infinite loops. Ever. And why is that so critical? Well, because Bitcoin is a decentralized network. Every single node, from a massive data center all the way down to a cheap laptop, has to independently check and validate every single transaction. And that guarantee of predictable, fast execution is what makes that global consensus even possible in the first place. So I'll just leave you with this thought. For years, people criticized Bitcoin's scripting language for being too simple, too limited. But when you really understand the why behind it, you start to see that this limitation, well, it might not be a bug at all. It might just be its greatest feature, the bedrock of security and predictability that makes this whole thing work.